It's recording. Okay. So hi, my name is Aneta Ochoa, and I'm going to be talking about density functional theory. First, I set some objectives. For this presentation, so that you can take something out of it. One of them is to understand what density functional theory is, identify the different types of density functional theory, and differentiate between the different types of functionals. I won't be going into depth into all the different types of functionals. I'm just gonna go over like the differences between them, and yeah. So first, I'm going to talk about what density functional theory is, and this is like a brief introduction to it. So it is a quantum mechanical modeling method used in physics and chemistry to investigate the electronic structure of a many-bodied system, such as atoms and molecules. And I really want to like sort of emphasize on the many body systems because there are different types. Of course, we know that hydrogen only has one electron, which is something that allows it to be sort of like a base for calculations such as this, because as we will see when we see the Schrodinger equation and stuff, which we've already seen with like Prakash's presentation, he really went into depth with it. That it gets really large with many-bodied systems. So first of all, I really wanted to have like a small introduction into quantum mechanics, even though I know it has been talked about in Prakash's presentation because he talked about the Hartree-Fock calculations, which are the ab initio, like some form of ab initio calculations, which as we can see, describe and explain the properties of molecules and atoms with their constituents using their electrons, protons, and etc. So there are, in quantum mechanics, there are sort of like the three main methods as to the analysis of these molecules. And as I mentioned before, Prakash talked about the Hartree-Fock, but there's also the Moeller-Plesset, and I'm going to be focusing on the density functional theory over here. So quantum mechanics is a science that deals with the behavior of matter and light on the atomic and subatomic scale. These methods here are all how do you say, part of the theoretical part of chemistry, right? As we know, like Dr. Jorgensen is a theoretical chemist and stuff. Yeah. Here, I just put like a little brief introduction as to what is the Schrodinger equation. I didn't want to go into depth into the equations because we saw it already. So it is used to solve a molecular system. And what you do is like in the computer, in the supercomputer, you input like as to what we see similarly with the calculations that we've done. Sort of in the problems that Dr. Jorgensen gave us, you input the coordinates of the molecule, the net charge, and the total spin, and then the computer gives you the output, which is made of the total energies, the weight, and the weight function, from which you a lot of the properties of the system can be calculated, such as like the heat of formation and all of that stuff that we really care for, like in this research. However, the Schrodinger equation, it's used to solve for a molecular system, but it can only be used with a single electron, right? Because as we saw previously, like in Prakash's equation, he explained it well, that it becomes really large when you have many electrons. And it's something that cannot be calculated obviously by hand. And even when you try calculating it with a computer, it takes a lot of the computational like energy. So things like the Hartree-Fock, the density functional theory. All of these methods are attempts to make this sort of theoretical calculations for energies to become more computationally like cost effective, right? We don't want to be wasting energy and money when we could find something that would be more effective. So okay, so here I'm just like going over it again. Multiple election systems can be solved through approximations to these numerical solutions, which again are the Hartree-Fock, Morley-Plesset, and density functional theory. So here I go a little bit more into, how the density functional theory is used. Excuse me. And it is used in the majority of the quantum mechanics calculations because it is really effective in what it does. And it is based on the electron density, which is a function of only 3 coordinates of the Cartesian plane. And this is basically, it says that instead of using the wave function, you use electron density, right? Later, I'm gonna go a little bit more in depth as to how they get here, but at the heart of it, which is why I put a heart, at the heart of it is the Hohenberg-Kohn theorems, which are sort of based as well in the Thomas Fermi theory for electron density. So I really wanted to introduce it here as well. So the theorems are, the first one is that the ground state energy, which is what we're looking for. You always want to find the ground state energy because with that you can do all of the other calculations. And it is a unique function. It says that it is a unique functional of the electron density. So it sort of kind of creates a relationship between these two things. And the second theorem, it says that the electron density that minimize the energy of the overall functional is the true ground state of the electron density that we're looking at. These theorems, of course, have equations, but I really didn't think that they would be like any important because we're not focusing on setting methods. We're focusing on calculating using the already made functionals that we have in our computers, right? But here, another thing about another sort of like step or base used in the density functional theory is the Born-Oppenheimer approximation. And this approximation, what it does is that it decouples the dynamics of the nuclei and the electrons by reducing the number of variables in the equation. Because we know that the nucleus, it's larger and sort of, when moving, right, slower than the electrons because we know that the electrons are small and fast. So it sort of like decouples it so that the study of the electrons and the energy of the electrons is easier, right? I put the equation here just because I wanted to highlight on this here and this here. So this functional here is the kinetic energy of the electrons. And then this functional here is the quantum electron interaction energy, right? I really want to like highlight those because they're useful for this next concept. Sorry, I have it on my iPad here and it moves. So the Thomas Fermi model, which I previously mentioned that Thomas and Fermi said the theory for electron density. This model says that the simplest approximation, for the kinetic energy of the electrons is an exact, is except for an infinite amount of uniform electron, it's exact for an infinite uniform electron gas. So it's later will come out as UEG. However, even the best existing approximations are only applicable to systems that are uniform with their densities and cannot describe chemical bonds properly. So basically, this is just another like example as to why the density functional theory had to be made, because there were no exact calculations that will give you the information that you want to get. So then this is sort of as the accepted model for density functional theory, which is the Kohn-Sham density functional theory, or DFT. And Kohn and Sham demonstrated that the kinetic energy could be accurately approximated by a single Slater determinant of orbitals, which is the one that we can see here, by describing a fictitious system of non-interacting electrons that has the same density as the exact electronic wave function. So basically what this means is that when they're running the calculation, they sort of put a guesstimate of the system and then they run it. And if they sort of end up having the same result as their original input, then they're like, okay, so our input is correct. If it's different, then it's sort of an approximation as to what they think would be an accurate input for their system. And it seems sort of like really complicated, but it's sort of what they could do with the calculations that they had. And the only unknown in the KS-DFT is the exchange correlation functional, which is this one. So basically, they input all of the rest of the information and then they get the exchange correlation functional. We talking about now of the density functionals, DFT functionals. So there are two routes that the DFT functionals can take, which are the non-empirical route and the semi-empirical route. So first I want to talk about the semi-empirical route, which uses a flexible functional form that's typically a power series with undetermined coefficients that enhance the variables based on physical ingredients and fitting the coefficients to accurate reference values. So here we can see that it uses reference values, and these are typically gotten from these right here. These are typically gotten from experimental results. So the non-empirical route basically means that no experimental results are used. The only things that are input into the system are quantum mechanics laws, right? And now here I want to focus on like the honorable mention. The paper that I used said that it would be a blasphemy not to talk about it. So I'm going to talk about John Perdue and Axel Beck. I think that's how you pronounce his last name. And their contributions to the non-empirical density functional, this is the one that we talked about, will be John Perdue. And for the semi-empirical density functionals, it will be Alex Beck. And their contributions are so impactful. Like these contributions, all of their work was done like 30 years ago. And even though as quick as technology like advances, their work is still used in nearly all of the popular density functionals that are current in computational chemistry right now. So I'm gonna explain a little bit about how DFT functionals sort of work and how they don't work. So a way that they don't work is that they cannot be systematically improved. So there's no way that you could go back and sort of like tweak things because there is no guarantee that using additional like factors could satisfy the more exact constraints or give a more flexible functional that will sort of account for all of the types of interactions that occur in a system, right? Because when you have a many-bodied a many-bodied system, there are a lot of differences within them. Like there's not sort of like this even and cohesive environment, right? So this sets it apart from the DFT from the wave function theory. It sets apart the DFT from the wave function theory. And in the wave function theory, there is this clear hierarchy that sort of allows for improvement within the models. For DFT, there's always something physical that's missing, right? And here, the DFT hierarchy, which is what we see right here, it's represented by the metaphorical Jacob's ladder that it was done by John Purdue. And as you can see, you have your base in like the exact Hartree-Fock world, and you ascend, quote unquote, to chemical heaven, which would mean that you will get really accurate and realistic results from the calculations that you're running for the energies and stuff like that. Yeah. So for the DFT functionals, we see that we have our ladder and it is composed of 5 rungs that correspond to increasingly sophisticated models for the unknown exchange correlation of a functional in DFT. And each one of them, as you go up, there is a new physical content that is missing in one of the lower rungs, which gives more accuracy to your results. So I'm gonna be talking about a little bit about these in a very like general way, because as we are not focusing on like creating new models or improving any of these models, I'm just gonna go give a little bit of an overview on each of the rungs that we have and sort of how they improve or try to improve them, right? So first we have the simplest one, which depends on the electron density, and it is known as the local spin density approximation. And these are exact for uniform electron gases. However, they are not really good for to calculate molecular properties. They tend to be very inaccurate. And this is due because of the non-homogeneity that we have in these models in their density distribution, right? Because of course, like models that aren't like systematically made aren't like perfect, right? And in order to improve this LDA, we go to the GGA, which is called the generalized gradient approximation. And what this does is that introduces a gradient that can account for these differences in the homogeneity, like the unhomogeneity, I think that's how you say that word, in the density. So it adds a density gradient so that it can take into account the different densities that we find in the model. And it gives a significant improvement for the LDA. However, there are things that the GGA does not take into account. And one of the additions that can be done to get more accurate results is the addition of the kinetic energy density. And then there's also a thing called the Laplacian of the density. However, the kinetic energy density is most commonly used. And this can be useful to detect electron delocalization in molecules, which is something very important, right? Functionals that depend on the kinetic energy define the third rung of the ladder, which is called the meta generalized gradient approximation, which is the one like what I just talked about, which is just the addition of the of that aspect of the kinetic energy density. But of course, there's things that the MGGA outperforms for the GGA, and that's the atomization energies and the barrier heights, and it sort of like gives a median range the readings for dispersion of the electrons. But there are three major limitations to the exchange correlation functional of MGGA, and that is that it is like it has some sort of errors, and these are the self-interaction error, like the interaction within the molecule, the model, the long-range dynamic correlation, or like dispersion, and the strong correlation. And one of the approaches to sort of fix this is creating a hybrid, which is sort of to replace the local exchange functional with the exact exchange functional, which would be the Hartree-Fock one, while still using a local correlation functional that gives exactly zero correlation energy for any one electron system. So basically, you sort of mix the local exchange functional with an exact exchange functional, and then you can kind of like mix those two and create these different hybrids that will give you more accurate results. And that is my presentation. And even like right now with the hybrids, there's also one called the global hybrid functional, which improve when compared to the local hybrid functionals. There is no perfect system or perfect method right now to calculate for all of these properties on large and complex models. So that's why it's like represented metaphorically by the ladder, right? The Jacob's ladder, because the hope is to get to a point where they can sort of create a new method, which would lead them to get accurate results for like the calculations that are run. But of course, there's still a lot of work to do in computational chemistry. However, that's not something that we're working in this lab. We're just using this set models to sort of get the properties of the molecules that we're being like asked to calculate. So that's my presentation. Thank you. I hope this was informative and hopefully a little bit entertaining. So thank you.